you know that before the dinosaurs, many other animals inhabited the Earth? When we think of prehistoric fauna, we naturally think of the famous Tyrannosaurus, Triceratops, Diplodocus, and Ankylosaurus. But life didn't begin with these reptiles and dinosaurs. Far from it. Dear travelers, welcome. Today we're off to explore the ancient world before the dinosaurs. What strange creatures inhabited the world's land masses and vast oceans before the age of the dinosaurs? But before you set off on your next adventure, don't forget to like the video and subscribe to the channel so you don't miss a thing. Thank you, and have a great trip! Everything has a beginning and an end. Life is a succession of eternal beginnings. For a long time, the appearance of life was a mystery. Then, through research and technological evolution, mankind managed to shed some light on the subject. Billions of years ago, the first microbial life appeared. As evolutionary processes continued, more complex organisms emerged. When and how? These were the questions that swarmed the minds of scientists in their quest for knowledge. These organisms hold the key to understanding our own origins. But the appearance of life goes so far back in time that it's difficult to find remnants of this distant past. Yet in 1946, a major event in the understanding of our history took place. Perhaps you recognize the place. We're here in Australia, more precisely in Ediacara, a mountainous region in the south of the country. It's here that fossils buried for millions of years will finally come to light and bear witness to their owner's presence on Earth. When our camera scans these rocks, at first glance they don't look any different from ordinary rock elements. But on closer inspection, with a more scientific eye, these rocks are quite extraordinary and unique. They preserve traces of life hundreds of millions of years old. Scientists have discovered animals like those at Ediacara elsewhere. So why is the Ediacara fossil site so important? Scientists have had great difficulty in locating these living organisms on a geological timescale. Without much conviction, but without being able to back up the period more precisely, these organisms were counted among those living in the Cambrian Era. The Ediacara fauna calls everything into question, or rather, it finally answers a fundamental question essential to understanding our history: the question of the evolution of life. Through studies of this site, stratigraphic and paleontological studies, as well as radiometric dating and analysis of the chemical composition of the rocks, scientists have finally been able to determine with greater certainty that these animals lived before the Cambrian. For many years, the transition from the Precambrian to the Cambrian was very unclear. Thanks to the study of this particular site, scientists are now uncovering a new chapter in our history. This is a major discovery. They have brought to light a new period in our history, the Ediacaran. This pivotal period between two eras epitomizes the emergence of complex life on Earth. The Ediacaran is therefore the period with which the Precambrian super-eon comes to an end. This super-eon, still largely unknown today despite fascinating recent discoveries, spans almost 4 billion years. It's the longest period in Earth's history. The Ediacaran represents a tiny part of it, but it provides a window into the mysteries of the period and a springboard to the next. While Australia has provided us with some slightly more precise answers, we now need to travel to England to deepen the scope of our knowledge of the period. In the 1950s, a number of discoveries were made, this time not to locate the fauna, but to give them a face. It was in Charnwood Forest, in Leicestershire, England, that a few specimens came to light. At the time, the site was considered to contain rocks so ancient that they date back to well before life began on our planet. Despite their great historical and geological wealth, they were of little interest to fossil hunters and paleobiology enthusiasts. With Ediacara having helped to shake up knowledge on the subject, young scientists, notably paleontology students Roger Mason and Tina Negus, decided to lead a number of expeditions. One of the first organisms discovered, very similar to some of the fossils found at the Ediacara site in Australia, was at Charnia masoni. It resembles a long, thin leaf of a sea fern. Despite its highly recognizable plant-like appearance, scientists have reason to believe that it is an animal. It was attached to the ground and fed through a filtration mechanism. In the silt assemblage, another fossil specimen is found 40 centimeters from the Charnia masoni fossil. It was discovered several years ago, in 2007, but it wasn't until 15 years later, in 2022, that it was actually identified and named. In the same year, it was named Aurora lumina attenboroughii, after biologist David Attenborough. According to studies carried out on this specimen, it was one of the very first cnidarians. This unfamiliar group includes animals such as corals, jellyfish, and anemones. This one is probably more closely related to the medusozoans. These animals are quite subtle to identify, hence the difficulties encountered with Aurora lumina. Indeed, their life cycle is complex and passes through different stages. When studying such ancient remains, it can sometimes be mistakenly assumed that one evolutionary stage is an animal, and that the next stage is another animal in its own right. In fact, it is merely an evolution of the first. To put it more clearly, it's a bit like looking at a tadpole and a frog differently, for example. Here, with our Aurora lumina, there's no question of a tadpole. In its first phases of life, it's a sort of mass anchored to the bottom of the sea. But during its sexual phase, it will detach itself and become a floating form. It is during this floating phase that it can reproduce. It's during this phase that it really takes on a jellyfish-like appearance. It has an umbrella-shaped body and stinging tentacles. Now there's no mistaking it. The specimen we found in England was in its ground-anchored phase, making it difficult to study from the right angle. In addition to its advanced age, Aurora lumina has other exceptional features. It is not only a very old living organism, but also one of the very first organisms with a skeleton. It has densely packed tentacles that move in water. It is also undoubtedly one of our planet's very first predators. In any case, it's one of the oldest we know of. The predator-prey cycle therefore began here, 560 million years ago during the Ediacaran. Using its tentacles, it captures passing food, in much the same way as corals and sea anemones do today. Since the Ediacaran period was first discovered and integrated into the thread of our planet's history, numerous discoveries have been made to support the seascape of the period. Although we still lack a great deal of information about this part of our history, there are many elements that enable us to understand more about our origins. Ediacaran animals were not nearly as developed and complex as they are today. They were also nowhere near as elaborate as the animals we encounter in the next era, the Cambrian. For the time being, nature seems to be drawing simple sketches of life. These animals bear no resemblance to our modern ones. It's true that we're a long way from mammals, reptiles, and fish, even if these animals are multicellular organisms of various shapes and sizes. Nevertheless, they are biologically indistinguishable and a real headache for scientists trying to classify them. Even today, this classification is still a matter of debate. For this reason, they are not really defined as animals per se, but rather as complex living organisms. Even so, their feeding habits are fairly basic. These proto-animals, with their soft bodies and no internal organs, feed via their cell membranes, which are their own bodies. These first complex life forms live exclusively in the ocean, and yet, no creature has managed to establish itself permanently on the continent. The Ediacaran fauna is therefore a marine fauna living in the Prototethys Ocean. These organisms were shaped like discs, slings, or feathers. They are soft and flat. They have no skeletons, which is what made them so difficult to discover, study, and visualize in 3 dimensions. All these specimens have contributed to the construction of today's world. They paved the way for the groups we know today, such as mammals, fish, insects, birds, and reptiles. This fauna, both simple and complex, in any case more complex than the first single-celled organisms, form the springboard for the emergence of the Cambrian fauna. The Ediacaran forms the basis of the luxuriant fauna to come. At the end of the Precambrian, the Earth underwent a number of changes. After a period of major glaciation, our icy Earth lost its white mantle, revealing a unique continent, Rodinia. From these desert lands, where only rocky stretches fill the landscape, we can see the ocean Morovia as far as the eye can see. Rodinia begins a slow but definite breakup. New continents take shape in the southern hemisphere, with Proto-Gondwana to the south and an archipelago of gigantic islands to the north, including Laurentia, Baltica, and Siberia. It's around this archipelago, and right up to the edge of Proto-Gondwana, that we find our famous Iapetus Ocean. In the shallows of this ocean, a biological upheaval takes place. If there is one period in Earth's history that we could describe as exceptional, it would undoubtedly be the Cambrian. Not because it represents the first period of the Paleozoic eon, but because it marks the appearance of the first ancestors of the plant world and of living beings, some of which are still present today. It's as if the Cambrian had changed the face of the world forever. During this period, which began around 539 million years ago, all the major forms of animal life were in the process of hatching. They were still exclusively marine, but they were flourishing, luxuriant. I almost want to say effervescent. It's a veritable explosion of life in the ocean, a festival of evolutionary processes, radiation, and species specifications. If we speak of a Cambrian explosion, it's because it was at this time that life experienced an unprecedented boom. It developed rapidly, but also diversified widely. Fossils of these species can still be found in various parts of the world, notably at the Burgess and Xinjiang sites. To make the most of discovering these species, rather than traveling to Canada or China, I suggest diving directly into the Lapidus Ocean 530 million years ago to meet a small handful of them. Let's begin our marine exploration in the heart of this flourishing ocean landscape. We can see the beginnings of the first coral reefs. They provide shelter for many animals, forming what could be described as the first marine ecosystem. As well as corals, we can also see a few sponges. These also contribute to the architecture of the seabed. In this maze of corals and sponges, we can see a crustacean ancestor, the Canidaspis perfecta. Like all the others you can see here, it is a benthic animal, meaning it lives on the seabed. The bottom is covered with small animals such as the olenoids trilobite, Opabinia, Hallucigenia, Wuwaxia, Branchiocharis, and Morella. As you can see, their shapes are extremely varied. There are many arthropods, including trilobites, crustaceans, and chelicerates, as well as mollusks such as gastropods, and a few brachiopods. Picaia is a bit special. It is probably the first to have a pseudo-backbone called a cord. This is not made of bone, but of cartilage. We'll see later in our journey that some fish have preserved this cord, notably the chondrichthyans. In short, the diversification of life is underway, and the foundations for a rich and luxuriant biodiversity have been laid. On the mainland, on the other hand, things are a little different. Apart from the occasional lichen, especially along the coast, there's nothing but rock as far as the eye can see. The ocean is and will remain for a long time to come the cradle of life. It's time to see what these animals will become in the next period, the Ordovician. "50 million years have passed, and the Cambrian chapter, rich and teeming with life, closes here to make way for the Ordovician." So here we are, more than 490 million years back in time. Some changes in flora and fauna are about to take place, and you'll see that this period is marked by major radiation in many groups. But before we look at these different developments, let's take a look at what the Earth was like at this time. You'll notice that for the moment, there are very few changes from the Cambrian period. To the south, you can see the supercontinent of Proto-Gondwana, and a little further north, the famous archipelago of islands comprising the continents Laurentia, Baltica, and Siberia. They are bordered by the Lapidus Ocean. While recent glaciation has led to a drop in temperatures in the south, temperatures remain mild and temperate in the north. The end of the Cambrian was marked by a minor extinction. Like all extinctions, this type of event leaves ecological niches vacant. A new order is established, and the species that manage to survive occupy these vacant niches. They evolve, specialize, migrate, adapt. We speak of radiation. These radiations were to be numerous throughout the Ordovician period. It has to be said that apart from this small extinction, another element enabled a new fauna to emerge and diversify. Various climatic events at the end of the Cambrian led to a drop in sea level. This meant that shoals were more extensive, offering new opportunities for living things to benefit from the sun's rays. If the Cambrian is described as an explosion of life, the next period is referred to as the Great Biodiversification of the Ordovician. We can see, for example, that plankton is growing and diversifying, a boon for trilobites. Brachiopod bivalves and crinoids also enjoy the menu. These groups are becoming richer and richer, and are now among the most present animals in the seascape. Corals, which also benefit from this abundant nutrient source, will be able to expand their territory. As you can see, these masters of marine architecture abound. They have everything they need to survive and thrive in the shallows. They form an ecological niche, an essential element of this new ecosystem, which is highly appreciated by many groups and will undoubtedly facilitate the emergence of new species. If you take a closer look at this reef, you'll notice that these corals aren't the region's only architects. Bryozoans are also present. The limestone skeleton invertebrates you see here are not plants but animals. Like corals, they live in colonies. During our Cambrian escapade, we discovered Picaia. It probably fed using its gills. Now, during the Ordovician period, with the help of various evolutionary processes, things have changed a little on that front. Ostracoderms, like Astrapus, now use their gills exclusively for respiration. Although the first Ostracoderms had a fish-like silhouette, their morphology was still very basic. They have no fins, for example. Nevertheless, they are able to move around using the rear part of their body, and this is undoubtedly what led to the evolution of the caudal fin. Poor swimmers living on the ocean floor, they were easy prey. Their only defense was armor. They had eyes, but again they weren't very well developed. Scientists believed they could see shadows, but very little detail. So they relied mainly on their vibration-perceptive bodies to keep them out of harm's way. Here's what we can say about their mode of movement and body shape. Now let's take a look at their feeding habits. As they are not yet equipped with a jaw, these fish have to make do with sucking up their food. As their food is rather abundant, they have plenty to eat. In this part of the ocean, rich in corals and ostracoderm fish, we can also see some much more aggressive animals. Yes, with a predator-prey cycle well established, it was only natural that such an abundance of filter-feeding animals should become a breeding ground for carnivores. There are cephalopod mollusks, but also arthropods of impressive size. Let's start with cephalopods. The main difference between these Ordovician mollusks and the animals of the previous era was their living environment. Until then, the fauna was almost exclusively benthic, i.e. it occupied the seabed. But here too, things changed during the Ordovician period. The first pelagic animals emerged, including cephalopod mollusks. Here we can see the two main groups of the period: the orthoceratids, characterized by long shells, and the lithoetids, characterized by extraordinary coiled shells. Able to swim in the heights of the sea, they are the great predators of this oceanic zone. These animals measure just a few centimeters. What's remarkable about them is their ability to build a new chamber whenever their growth requires it. The rear compartments, which the animal occupies at a juvenile stage, then change function. If they no longer provide shelter for the animal, they can be used as ballast to move vertically through the water. Our other ocean predator is an arthropod. Its name sent shivers down the spines of Ordovician animals. It was a terrible predator. It's called the Eurypterid. This is the sea scorpion you see here. It's actually a cousin of spiders and scorpions. Its shape has earned it the nickname of sea scorpion. Pentacopterus, at 1 meter or 3 feet long, is fast becoming the great terror of the seas. When you see the physical characteristics of our previous animals and observe the physical capabilities of this Eurypterid, you quickly understand that the prey that crosses its path doesn't stand a chance. It has a solid carapace and much more developed legs and eyes. What's more, as you can see here at the front of its head, it has pincers. This means that its limbs are specifically designed for hunting. Once the prey has been seized, there's no chance of it getting away. One of the marine arthropods that appeared during the Ordovician period is still present today. Do you know which one? Here's a hint. It's blue-blooded. Can't you tell? It's the horseshoe crab. Yes, this little animal has survived the ages. Despite all the geological and climatic upheavals we've seen, it has managed to survive right up to the present day. Quite an achievement. Now let's see what's in store for the Silurian. Now that we've crisscrossed the four corners of this ocean, how about seeing what's going on in the great outdoors? At first glance, there's nothing really different from what we saw in the Cambrian. But if we equip our camera with a sufficiently powerful zoom, you'll be able to see the first single-cell spores. What does the presence of these spores mean? Undoubtedly, a more complex form of plant life is emerging. Until now, life on Earth has been exclusively aquatic. But during the Silurian, the world of living things took a new turn. The Silurian may be the shortest period of the entire Paleozoic, but it is just as important as the others. Quite the contrary. The Earth's soil welcomed its first hosts. Still shy, they slowly but surely colonized this new environment. The landscape becomes very different. After being devoid of all possible life, the first inhabitants of the Earth's soil cohabit to form the very first open-air ecosystem. But before we take a closer look at what's happening on the surface and who these first settlers really are, and before we return to the sea, the cradle of life that will undoubtedly give us the answers to what brought the animals to the surface, we need to take another look at the climate and geology. To understand the Silurian inhabitants, we need to understand the environment in which they live, don't we? So let's get back on track. The Silurian chapter opens on a dramatic note. The previous period ended with a major biological crisis, a mass extinction so great that it left the living world in shambles. It seriously shook the established order. In the end, many species and even groups disappeared completely. But the cycle of life is gradually returning to equilibrium. So, 440 million years ago, at the beginning of the Silurian period, nature began its slow reconstruction. And speaking of rebuilding, there's another element, this time a geological one, which is also beginning to rebuild. The archipelago we've seen so far, Baltica, Siberia, and Laurentia, will gradually shift to form a new supercontinent, one that scientists will call Laurasia. Bringing land masses together in this way obviously changes the face of the Earth once again, but not only that. If we get a little closer to the ground, we can also observe how the collisions between these lands have an impact on the very geology of the continent. Mountains rise from the ground, giving rise to one of the very first mountain ranges, the Caledonian Chain. A little further north, the Hercynian Chain, far from having fully emerged from the depths of the Earth, can also be seen, giving a glimpse of its future silhouette. In the blue immensity, things have changed too. In the Ordovician, a great period of glaciation marked the second era of the Paleozoic. In the Silurian, these ice sheets are melting and the waters are rising. This higher ocean level will be a godsend for certain species, who will take advantage of the opportunity to carry out a major evolutionary radiation and appropriate new ecological niches. It's time to embark on a fascinating underwater journey into the Silurian Ocean. The Iapetus Ocean, bordered by the Proto-Gondwana and Laurasia, is teeming with life. Crinoids, brachiopods, trilobites, nautiloids, and of course Eurypterids rule the roost. Eurypterids could even be given the title of King of Iapetus, as they thrill every nook and cranny of the ocean. They were already impressive in Ordovician times, but the Silurian seems to multiply the already extraordinary physical capacities of Eurypterids. They are disproportionately large. Giant species measure as much as 2 meters or 7 feet in length. Pterygotus is one of the elite sea scorpions. With its powerful claws, solid carapace, and numerous legs, it can take on any benthic animal that crosses its path. The Eurypterid reign is such that scientists believe that some species have not confined themselves to the aquatic world, but have even taken a few steps on the surface. The mystery remains. Another emblematic group of the period was fish, which also underwent a tremendous radiation. Placoderms entered the aquatic scene. Remember, during the Ordovician period, ostracoderms represented a major evolution in the fish kingdom, but they were still agnate, i.e. jawless. This time, placoderms fall into a new category, that of gnathostomes. These fish have jaws. That's going to change a lot in their diet. But don't confuse the two. Jaws do not mean teeth. Silurian placoderms may not have teeth, but that doesn't mean their jaws are any less powerful. Their bony outgrowths are still sharp enough to take on small prey. They also have a protective dermal plate on the front of their body, scales on the rear and fins. Placoderms thus became serious predators. Now that nature has reclaimed its rights, prey is plentiful, helping this group to expand throughout the ocean. Let's spend a few more moments in the midst of these fish to talk phylogeny. As you can see, there are many more species than in the previous period, and the fish will also diversify greatly in the periods to come. Gnathostomes, the jawed fish, gave rise to several lineages that we still know today. Gnathostomes gave rise to two major groups in the first part of the Silurian: chondrichthyans, cartilaginous fish, such as sharks and rays, and osteichthyans, bony fish. They in turn gave rise to two other groups during the next period: the actinopterygians, ray-finned fish, and the sarcopterygians, flesh-finned fish. The latter would later pave the way for the crossopterygians, which in turn would give rise to an essential group that we would meet again and again in the next period, the Devonian, that of the tetrapods. By observing these different lineages, you'll understand why the Silurian lays the foundations of the future aquatic world. But the period is also a milestone on land for other reasons. Let's go back to the surface for a moment to find out why. On land, since the start of our Precambrian journey, we've been faced with a desolate landscape. It has to be said that for the moment in the Silurian, this is still somewhat the case. The environment remains rather hostile, even if the lichen is no longer completely alone, since moss has managed to make a small place for itself in the restricted universe of terrestrial plants. To see the nuances between Ordovician and Silurian, you need to get closer to the coast. They represent a small hope for the group of plants in search of diversification. With the movement of water, particularly the ebb and flow of the sea, sediments were deposited along the coast. These sediments were to play a vital role in enabling the first plants to settle on the land. If there were a name to remember here, it would be Cooksonia, the first plant to enjoy the fresh air near the coast. At the end of their long stems, these plants are equipped with spores, which they release into the air. This enabled the plant to reproduce and colonize a wider area. In the Middle Silurian, nature gave these plants a further boost, enabling them to breathe ambient air thanks to the presence of stomata, small holes at the edges of the stem. This new plant cover, minimal and primitive though it may be, and the corpses washed ashore, suggests that small arthropods may have seen here new ecological niches to conquer. Phylogenetic reconstructions have enabled scientists to date the appearance of the first insects well before the Upper Devonian, probably in the Silurian. The reasons for this lack of fossil evidence are still a matter of debate, but scientists believe that insects undoubtedly played a part in the plant boom that took shape in the Devonian. One example is Strudiella devonica, a small creature that looks like a pseudo-grasshopper. This animal has all the characteristics of a terrestrial insect, but no morphological features or organs that would allow it to adapt to aquatic life. Let's follow in its footsteps, as it leads us to the next period, the Devonian. We're now in the Devonian, a period that's also full of twists and turns. On the geological front, things are about to get a whole lot messier. Until now, the great continent of Proto-Gondwana was located in the southern hemisphere. Now it's gradually sliding northwards, except that to the north we already have the continent Laurasia. Impact is therefore inevitable. The Panthalassa Ocean covers most of the Earth. This ocean is teeming with life. We left it in the Silurian, with a wealth of radiation and a rich variety of species. It's been millions of years since the Earth experienced a major biological crisis, so life is quietly going on. But while many of the species and groups from the previous period are still with us, there are also a few new phenomena. On land, we can see that the plant cover is more diversified. This is due to the arrival of ferns and lycopods. The latter are the very first plants, to our knowledge, to be considered arborescent. Initially, plants were mainly found along the coasts and the plant strata remained fairly low, but they soon colonized a wider area and, above all, gave rise to the first forests. Here we can see that vegetation can be divided into several different levels. So why do plants reproduce so quickly? Well, the answer is simple. Plants developed new reproductive strategies, climatic conditions were ideal, and above all, there were no herbivores. For the time being, no animals are feeding on these plants. There was nothing to hinder their expansion. The forest came to life, spreading its arms further and further out, embracing territories that had hitherto known nothing but dust and rock. This new vegetation, now partly leafy, will be able to consume carbon dioxide and release oxygen. The close relationship between vegetation and atmosphere thus began during the Devonian period and continues to this day. Time to return to the ocean. As we have seen, gnathostomes were to play a major role in the fish world, giving rise to several phyla, including the tetrapods. Among these gnathostomes are the placoderms. Although they were already present in the Silurian, it was in the Devonian that they really developed. Their new physical characteristics enabled them to conquer large territories. A new world opened up to them. Benthic fish used to remain at the bottom of the ocean, but thanks to their fins, they now become pelagic fish and take advantage of the water column. With food in abundance and no real competing predators at the moment, this is an opportunity to be seized. As we've seen, placoderms are jawed fish with pseudo-teeth, a kind of bony outgrowth. This means they can easily attack small prey and even have a field day. Just look at the most monstrous of them in action, the famous Dunkleosteus. Placoderms have a major place in the ocean, as these fish have new physical abilities. This time it's not in movement, but rather in breathing. They have lungs. This means that these fish are able to breathe at the surface. At the surface. Until now, no animal, with the possible exception of a few arthropods and insects, had achieved this little feat. This ability will come in very handy for these aquatic animals. At the moment, you're probably thinking that for a marine animal, breathing underwater was quite sufficient for survival, and you'd be right. But the problem for some of our lungfish is that precisely for their own survival, in the face of increasingly ferocious predators, they are sometimes forced to leave the vast ocean and seek refuge in swamps and mangroves. In this new aquatic world of roots, branches, and other obstacles, it's hard to get around. Their fleshy fins will be the first pillar on which they can rely to get by. They will help them to pull themselves up, hold on, push themselves. To be more efficient, the evolutionary process kicks in. Towards the end of the Devonian period, fins resemble pseudo-legs rather than fins in these animals. They can almost be described as tetrapodomorphs, so close are they to the tetrapods. Meet Tiktaalik. With its flat head and eyes above the skull, you'd think it would breathe from time to time at the surface. He moved through shallow, brackish water. Open air was therefore the best option for taking in oxygen. But it doesn't just float in these waters. It also occasionally puts its paws down on dry land. It has a neck, pseudo-fingers, lungs. With all these advantages for walking on land, it would have been wrong not to take the plunge. For the time being, animals like Tiktaalik remain exclusively aquatic and only take advantage of their ability to move around on land when absolutely necessary. Nevertheless, it paves the way for others, notably species from the late Devonian period, who clearly wish to dominate land rather than the aquatic world. These are stegocephalic tetrapods. Acanthostega, for example, prefers dry land to the sea. Acanthostega is not alone on this shore, however, with insects, scorpions, and even a few spiders also taking advantage of the plant cover. But, following this first step by an animal on dry land, and despite the richness and beauty of the nascent forest, Devonian biodiversity is about to collapse. The chapter closes with a new biological crisis, a major mass extinction that will wipe out a large number of species. What will bring nature back into balance is vegetation. Vegetation cover, which is less impacted, undoubtedly helps to clean up the gases partly responsible for climate upheaval and the biological crisis, by pumping out carbon dioxide and releasing oxygen. It is within this salvific plant cover that we will be able to enter the period that awaits us, the Carboniferous. We've come a long way on the timescale, but we're still a long way from the time of the dinosaurs. We now find ourselves 360 million years ago, in the aftermath of the second mass biological crisis. We have left behind 4 Paleozoic periods, and the last Precambrian period, the Ediacaran. The 5th Paleozoic period, which now welcomes us, has seen many events that will forever change the face of the Earth. First of all, the Carboniferous is linked to a physiognomy well known to the general public, Pangaea. The continental waltz played out a new score and reshuffled the cards of the Earth's geography. Pangaea, this unique supercontinent, took shape during the Carboniferous period. Towards the end of the Devonian, we had already seen that plate tectonics had brought the 3 islands of the archipelago together to form Laurasia, but also that Proto-Gondwana was slowly deviating northwards towards Laurasia. They would link up, unify, and eventually form a single landmass, Pangaea. It's pretty crazy when you think about it, to think that at that time there were no borders, not even the ocean, separating us from the 4 corners of the world. This is what the Earth looked like 340 million years ago, a continental block in the middle of an infinite ocean. On this vast land, we find a vegetation cover that had already expanded considerably in the previous period. But the process seems to have continued well into the Carboniferous. Take a look at these plants. A small revolution has taken place here. Gymnosperms are emerging. These are plants with naked ovules. Until now, we've only talked about spore plants, but this model of reproduction has its limits. With its warm, humid climate, the Carboniferous favored the emergence of this new reproductive process, that of the seed. As a result, new arborescent plants grew up in this vast plant cover. Cycas, lycophytes, and ferns developed, sometimes reaching heights of 30 meters. The race for light begins. Plants, much more diverse and luxuriant all over the continent, pump out carbon dioxide and release oxygen. While oxygen levels soar, CO2 levels fall sharply. The result is a global cooling of the Earth's temperatures. During the Carboniferous period, a period of glaciation set in, which did not end until the following period. However, this did not prevent life from growing. But let's get back to CO2 and oxygen levels. It's the impact of oxygen levels that's most interesting to analyze here. At between 30 and 35%, it's well above the current 20%. And this difference will play a major role in one group in particular, that of terrestrial arthropods. Do you have any idea what this means for this group? No? If I tell you that the Carboniferous period is often referred to as the era of giant insects, does that put you on the right track? Yes, little beasts no longer than an inch today would admit to quite exceptional lengths during the Carboniferous. And according to the scientists who have worked on the subject, it could well be the high oxygen levels that were responsible for their disproportionate size. In the lush vegetation of the Carboniferous, we find the giant dragonfly, Meganeura, with a 70-centimeter wingspan, as well as a 75-centimeter long scorpion, Pulmonoscorpius. Not to mention the Arthropleura centipede, which can reach 2.7 meters in length. As for the fauna, we can see that things have changed here too. After the biological crisis, nature had to rebuild everything. And reconstruction means new things. When certain species disappear, ecological niches are left vacant. This gap must be filled to restore harmony. Species that have managed to overcome the crisis and survive have plenty of time to fill the gap. However, nothing is certain. One of them must succeed in imposing itself more than the others through specialization and evolutionary radiation in order to fully integrate its new environment. This is what has enabled a group that had been lagging behind to come to the fore. In the Devonian Ocean, if we caricature and simplify things a little, there were two major ecosystems, that of benthic animals and that of pelagic animals. On the seabed, for example, we find echinoderms, crinoids, and brachiopods. In the pelagic zone, we find aquatic vertebrates, fish which we've talked about a lot in the previous period. These are the placoderms. They had completely overshadowed the presence of the ostracoderms, such was their development and progress. Although the placoderms were joined by the chondrichthyans in the gnathosomes, the chondrichthyans had a hard time making a real place for themselves in the ocean. Placoderms reigned supreme and were formidable predators. Despite their formidable radiation and physical prowess, they were unable to overcome the Devonian crisis. As a result, they left a vacancy in the water columns of the oceans, and it was the chondrichthyans who seized the opportunity and settled in this new ecological niche. Today they are considered distant cousins of sharks. Of course, these proto-requins needed to find abundant food to perfect their radiation and ensure their development and diversity. This was made possible by another group, the actinopterygians. Radiate-finned fish also took advantage of the aftermath of the crisis to undergo extensive radiation and, consequently, extraordinary diversification. Vacant ecological niches, food galore. Everything is in place for these proto-sharks to explore and become the new kings of the oceans. Even if the aquatic landscape is interesting and highly diversified, we're going to have to leave the ocean once again to return to dry land. Yes, there's a particular event that characterizes the Carboniferous that we haven't yet taken the time to mention. When Proto-Gondwana and Laurasia collided, the creation of Pangaea was not the only consequence. Indeed, a phenomenon of such magnitude invariably leads to equally impressive events. As a result of this collision, one of the longest terrestrial mountain ranges our planet has ever known was born, the Hercynian chain. Since the supercontinent broke up again, a small part of this orogeny can be found in various parts of the globe, but it originally formed the junction between Proto-Gondwana in the south and Laurasia in the north. It is estimated to be almost 5,000 kilometers long and at least 700 kilometers wide. When we said just a few minutes ago that the single continent knew no borders, we may have been speaking a little hastily. The natural frontier is a real impenetrable barrier. As a domino effect, this colossal orogeny will have multiple consequences. First of all, at the foot of these mountains, the soils quickly subside and accumulate sediment. These sedimentary basins can be flooded, as they form a kind of basin. And to say the least, there's no shortage of rainfall on this side of the mountain. The vegetation cover, the low-lying plants and the forest become very swampy. Different layers of humus, mud, dust, and sediment accumulate. Unlike today, with the help of fungi, the plants won't rot as they do today, but benefit from another phenomenon known as carbonization, the transformation into coal. It was this process that gave the period its Carboniferous name. Buried under sediments without oxygen and subjected to soil pressure and heat, plant debris slowly transforms into peat, then lignite, coal, and finally anthracite and graphite. While we're on the surface, let's take a moment to recall the last event of the Carboniferous period. We had to save the best for last. In Devonian times, the few appearances of tetrapods on land were still timid. But with life having been exclusively aquatic for billions of years, it's hardly surprising that it took a few million years for life to finally establish itself on dry land. Many amphibians, stegocephalan tetrapods, will become increasingly terrestrial. But for this to happen, new reproductive capacities had to come into play. The biggest problem for these animals was the fragility of their young. Always accustomed to laying their eggs in an aquatic environment, water was the ideal protective environment and was able to withstand shocks. On land, things are very different. To remedy this, nature has once again redistributed the cards and favored the appearance of the shell egg and amniotic fluid. The possibilities for survival on land increased tenfold, and many species were finally able to free themselves from the aquatic environment and live exclusively on land. It's on this pink amphibian notebook that we'll continue our journey to the Permian, which now awaits us. We're entering the very last period of our journey on Earth before the dinosaurs. A few million more years separate us from these emblematic Mesozoic animals. We are about 300 million years ago, at the beginning of the Permian. The Permian, the last period of the Paleozoic, joins the Mesozoic and the arrival of the Triassic. There are still almost 47 million years separating us from the Triassic. During these 47 million years, you'll see that the foundations of the Mesozoic are being laid, and that many changes and upheavals will take place. Climate, geology, biodiversity, the entire biosphere and everything connected with it will be turned upside down. And that's just what's needed to usher in the super eon best known to prehistoric animal lovers, the Mesozoic. Let's start by talking geology. We've seen that the continental waltz is already well underway. Pangaea was formed, and new orogenies with all their consequences followed. But it wasn't just on land that Pangaea had a major impact. In water, too. The sliding of the continents gave rise to a new ocean, the Tethys. The C-shaped Pangaea embraced, almost encircled, a small piece of the Panthalassa. It was this famous little piece of the Panthalassa Ocean that became the Tethys. You'll hear a lot about this ocean, especially the marine fauna of the Triassic, Jurassic, and even Cretaceous periods, during which it became a veritable marine breeding ground. By the Permian, Tethys was already a rather rich ecosystem. Why here? Erosion of the surrounding mountains and coasts feeds the ocean and enriches this aquatic universe. The sediments encourage the development of marine plants, which in turn benefit the first links in the chain. The Tethys Ocean is dotted with coral reefs. They can be found in large numbers, spread out over many parts of the ocean. This seascape is home to many benthic animals. These include the trilobite, of course, but also other small arthropods, brachiopods, and echinoderms. In the pelagic zone, we find cephalopods, various mollusks, and numerous goniotites, as well as many fish. As they are today, reefs and pelagic zones are very rich and diverse ecosystems. The ocean is teeming with life. Wherever you look, everything seems to be bustling. But while these images are magnificent, when you think of prey, you also think of predators. As we have seen, the chondrichthyans of the previous period gradually rose to the top of the podium, replacing the extinct placoderms. Now, in the Permian, things aren't much different. They remain incredible predators, and if possible, have become even more terrifying. Among them, the most impressive group is undoubtedly the hybodon. Like Hybodus, the hybodon has the huge advantage of occupying both salt and fresh water. Not far away, we find another predatory group, the xenosanth, also capable of surviving in both fresh and salt water. Both are perfectly equipped for swimming and predation, making them veritable terrors of the seas. The most emblematic of them all, however, is the helicoprion. It's a veritable marine phenomenon in its own right, intriguing fans of prehistoric animals. Its special feature is an astonishing circular jaw. Others, less frightening at first glance, are indeed large predators. Like this Genassa bituminosa, a petolodont. Well camouflaged on the ocean floor, this benthic predator is as good at camouflage as it is at surprise attacks. It's a subtle blend of sawfish, skate, and sole. But let's return for a moment to the heart of Pangaea, to a place also evoked during the Carboniferous period, the Hercynian chain. Over thousands of years, these high mountains have created sedimentary basins and marshy areas. That's where we left off when we investigated the subject. As you now know, it was undoubtedly one of the longest and most extensive chains in its time. We didn't mention height, but it did measure up to 6 kilometers in altitude. And that's what we're going to remember about the Permian. They rise so high in the sky that they slow down the clouds' course, not to say block them almost completely. The result is a high natural boundary that sets the pace for the climate on both sides. The northeastern slope is warm and humid, benefiting from abundant rainfall. On the other side, on the southern slope, the climate is hot and dry. No clouds cross the border, so no rain floods this thirsty land. During the Permian, there were clear climatic zonations, with luxuriant vegetation in the north and a rich and varied fauna, while in the south, the few species that managed to survive here were endowed with very specific abilities to combat the difficulties they encountered. Added to this is global warming, which is also drying out part of the continent. During the previous period, the climate had cooled considerably, notably due to vegetation. An ice age even extended over the entire period. In the Permian, however, this ice age is gradually coming to an end. In fact, the climate was nowhere near that of the previous one, more akin to that of a greenhouse, as the heat was dry and stifling in places. The first savannas and deserts are replacing areas that were once considered tropical because of their warm climate and high humidity. As spore-bearing plants are dependent on water to reproduce and develop their territory, it is the seed-bearing plants that will manage to thrive during this climate change. So how is wildlife coping with these new geological and climatic conditions? Let's return to a group we left behind earlier, the stegocephalan tetrapods. We left them on a major event for the species, the arrival of the shell egg and amniotic fluid. They thus gave birth to a new clade known as amniotes. These amniotes were to give rise to two new lineages that would form a large part of the terrestrial fauna of the future: the synapsids and the sauropsids. You'll be hearing a lot about these clades in the periods that follow, as they will make up a large proportion of the families and species living on the continent for millions of years. But let's get back to the Permian and the specimens of the time. The sauropsids form the clade that will lead to reptiles, probably originating from Hylonomus lyelli. The synapsids, for their part, gradually lead to the mammalian branch, perhaps beginning with Archaeopteryx florensis. The latter belongs to the Pelycosaur group. It is, however, little known to the general public. Another member of the Pelycosaurs which actually lived in the Permian, unlike the earlier Archaeopteryx, is the Dimetrodon. Its distinctive fan-shaped dorsal fin is easily recognizable. While many Dimetrodons, like Sphenocodon, are carnivores, there are also species of synapsids that are hardcore vegetivores. A cousin of the Dimetrodon, Edaphosaurus, adopted this very diet. Also in this category are the casids. Most of them, despite their close links with mammalian phylogeny, remain very reptilian in appearance. Gait and posture, for example, are fairly typical of reptiles. On the other hand, the last third of the Permian saw the emergence of a new clade and clearer evolutionary perspectives. The dinocephalans, gorgonopsians, and diconodonts already display more pronounced characteristics. Later still, the resemblance becomes almost striking. Thrinaxodon is a fine example. We can see that the position of the limbs, the general silhouette, the mouth, the dentition, and even the hairs are slowly but surely moving towards mammalia forms. Let's now take a look at the evolutionary prospects of the second clade, the sauropsids, i.e., the reptilian branch during the Permian. It took a little longer for the sauropsids to diversify and truly find their place on the continent. While synapsids began to diversify at the beginning of the Permian, sauropsids waited until the middle or end of the Permian. Many of them adopted a vegetarian diet. Examples include the Procolophon group and the Periosaurs, including Scutosaurus. Gradually, sauropsids gave rise to a new clade, the diapsids. Diapsids have two temporal fossae and will encourage the expansion of a large number of species, notably the Archosauromorphs. They are still far from having all the characteristics of the Archosaurians to come, but they seem to be at the origin of this promising new lineage. Like Proterosuchus fergusi, the Proterosuchidae group and more advanced forms were originally crocodile-like in silhouette, with an undulating gait and long snout. It was not until the following period that these groups led to more diversified Archosauromorph grades with quite different silhouettes. Another interesting point to note about the sauropsids, the reptilian lineage, is the specialization of certain species. The number of predators on the continent is increasing all the time. To protect themselves, some reptiles are becoming arboreal. At least this is the serious hypothesis put forward by the scientific world. But these tree-dwelling animals don't stop there. To move from tree to tree, they've developed the ability to glide. Such is the case of Coelurosaurovus. It is undoubtedly one of the first to be capable of this kind of feat in the air, thanks to the membrane attached to its sides. Not so long ago, we described the Tethys Ocean as a marine fish tank. On land, this fish pond is found in the trees, which are teeming with insects of all kinds, especially in the canopy. But until the arrival of these gliding reptiles, no predator occupied this ecological niche. These reptiles, true pioneers of the air, find both abundant food and shelter from predators here. If the recipe works against the famous ground-dwelling pelycosaurs, it won't protect many of them from the biological catastrophe to come. Whether in the heights, on the ground, or even at sea, mass extinction will strike a large number of groups, families, and species. Fauna and flora are going to be hit hard by several catastrophes, which coupled together will lead irreparably to an unprecedented biological crisis, with 90% of species disappearing. Several hypotheses have been put forward concerning the origins of the catastrophe. While the question is still open to debate, some of the answers seem plausible. Research is continuing, and we'll no doubt learn more in a few years' time. Current hypotheses include a collapse of the ocean floor due to a lack of renewal of the Earth's crust, resulting in fragility. The weight of the oceanic ridges responsible for the collapse of the seafloor means a drop in sea level of almost 250 meters, or 820 feet. That's huge! The hypothesis of volcanic eruptions in Siberia is also interesting. Large, long, and intense, they will create faults stretching for hundreds of kilometers and no doubt release very large lava flows known as traps. These will last 1 million years. 1 million years during which tons of lava, but also tons of rock, dust, and gas, are released. Imagine the consequences of eruptions on such a scale and over such a long period. Chaos reigns over thousands of square kilometers. Fires break out. The air is totally unbreathable. Everything is burnt or swallowed up by the lava. Accumulated gases heat up the atmosphere, making it stifling. Volcanoes release massive quantities of carbon dioxide, while the ocean releases a greenhouse gas responsible for global warming, methane hydrate. As long as it is kept at a sufficiently low temperature, methane hydrate remains in a solid state. As global warming progresses, it becomes gaseous and spreads as methane. The Earth's temperature rises by more than 10 degrees Celsius, or 18 degrees Fahrenheit. This is enormous. The vast majority of terrestrial species will succumb. Such a discrepancy is dramatic, even chaotic for the entire biosphere, which is impacted on every scale. 90% of marine and terrestrial flora and fauna will disappear. If we consider only marine species, which are even more affected, the figure rises to 96%. One explanation for the discrepancy is water temperature. The warmer it is, the less oxygen is dissolved in the water. This means that the aquatic environment becomes almost anoxic, and therefore unbreathable for most species. The continent finds itself as if enclosed in a greenhouse, also suffering the onslaught of heat, drought, and fire. The rain could have been providential if it hadn't been mixed with the sulfur dioxide released by the volcanoes, making the rain acidic. Plants, terrestrial and marine fauna, suffered directly from this acid rain, which polluted everything in its path. According to some scientists, it would take around 4 million years for a biodiversity as abundant and rich as that of the Permian to be truly established in the Triassic, the era following the mass crisis. However improbable it may seem after the catastrophic scenario described above, a few groups managed to survive, notably the Archosauromorphs. This group will gradually lead to the dinosaurs. But that's another story. In the first part of the Triassic period, temperatures rose sharply. However, from the second period onwards, temperatures softened markedly. This decline continued during the Jurassic, but temperatures rose again somewhat during this period, mainly due to the terrestrial activities mentioned above. There are no polar caps yet to cool the Earth a little and slow down the sun's rays. Nevertheless, the climate is quite favorable to vegetation, and by extension, to the land animals that benefit from this plant cover. The Jurassic was hot and humid, unlike anything we experience on Earth today. This climate favors the expansion of flora. The plant cover is lush and well developed, allowing wildlife to fill numerous ecological niches. Look how incredible the Jurassic forest is. The landscape before us is simply magnificent. After such a crisis, such dense, lush plant cover is reassuring. A few million years ago, the scene was very different. All was desolation, utter chaos. This time, life seems to inhabit this forest. Let's begin our journey in the heart of this undergrowth. Afterwards, we're sure to meet some of the forest's inhabitants and discover some emblematic Jurassic species. In what landscape did our famous Jurassic dinosaurs evolve? To understand the future diversification of dinosaur species, it's important to know not only the context, but also the world in which they evolved. As we've seen, the latter benefited from a lush vegetation cover. But what does it really look like? From small bushes to large trees, vegetation offers multiple ecological niches for insects and other vertebrates. Vegetation supports herbivores, but also small carnivores that feed on insects, for example. Other predators take advantage of the abundance of small carnivorous and insectivorous prey to feed in their turn. The large carnivores themselves feed on them, and the circle is complete. In other words, a complete food chain is created thanks to all the plants you can see in front of you. In the forest, you'll find a bit of everything, from herbivores to carnivores, insectivores, and even omnivores. This dietary diversity is made possible by the wide variety of vegetation and environments found in the Jurassic. You have to go deep into the forest to understand this. Once in the undergrowth, you can see not only the richness of the plant cover, but also the different strata of the forest, from the lowest and fullest to the highest and sparsest. You can also see how varied the genera and species are. To get to the heart of Jurassic vegetation, let's start with ferns. Yes, they're still with us today, as they may have been in the past, and they're even benefiting from new evolutionary radiations. They make up a large part of the plant cover of the period. Within this large group, there are many families, genera, and species. All families, sometimes quite different from one another, find their place within a particular ecological niche. These differences in ferns also lead to diversification in the insects and small animals that depend on them. Among Jurassic ferns, we can cite several families, such as Glycania truncata, Osmundastrum, Dipterodaceae, while other, taller ferns, such as Dixonaceae and Cyatheaceae, are also well represented. The great diversity of these ferns plays a decisive role in Jurassic forests, as we have just said, as they form the basis of certain ecological niches. But their position in the forest also explains why they so perfectly embody this role in the ecosystem. Ferns are part of what we call the lower strata of the forest. To put it another way, they form a sort of green meadow in the undergrowth. It's a green paradise for insects, but also for small animals, which find shelter and food in abundance. Although small, not always, ferns are also home to the giant sauropod family. But we'll come back to that a little later, once we've completed our overview of Jurassic plants. During this period, ferns were abundant, but there were also many other plants. After the ferns and small bushes that form the undergrowth, there's a middle stratum and a higher stratum that make up the forest proper. This Jurassic forest is luxuriant and abundant all over the globe. Today, it's hard to imagine that vegetation could be so abundant all over the Earth, as different continents and geological zones embody different types of climate and therefore vegetation. But in the Jurassic, even on the fringes of present-day Greenland, known for its ice and biting cold, vegetation was rich and well-developed, unlike today, when it is rather low and sparse. Three main groups of arborescent plants can be identified in the Jurassic. The first group comprises conifers, also known as pinophytes. This group includes the Cheirolipidaceae, a family that is now extinct. The Araucariaceae and Podocarapaceae, on the other hand, are still around today. Pinophytes are large trees. They are easily distinguished from others by their cone-shaped fruit. These cones serve as the plant's reproductive organs. On this tree, some cones are male, others female. These trees are called gymnosperms. Reproduction requires a little help from Mother Nature, particularly from the wind, but also from a few insects of the Mecopteran family, which have been active since the Middle Jurassic. They also provide an ecological niche for small insectivorous animals that settle in the forest. Everything is linked in nature. The great advantage of these pinophytes is their ability to establish themselves in a wide variety of environments, even the harshest. In this way, they have managed to colonize a large part of the world's landmass, even intertropical regions or salty environments, near coasts and maritime zones, for example. But this will not be enough to compete with angiosperms, the flowering plants that will soon occupy a large part of their territory. In addition to pinophytes, the forest is also populated by ginkgophytes. These species of ginkgos are the dominant trees in the canopy. They can reach up to 40 meters or 130 feet in height. Ginkgo digitata and adiantoids can be seen in this forest. Digitata trees have fan-shaped indented leaves. These species thrive in tropical and semi-tropical climates. The absence of cones and their famous palmate leaves distinguish them from previous conifers. These species will also provide new opportunities for the young fauna that gradually settled on planet Earth during the Jurassic period. Let's return to the lower forest stratum. In this region, it is also colonized by another type of plant, the cycads. The most dominant and emblematic group of the period is undoubtedly the so-called cycadophytes. Cycads are far from reaching the heights of the previous group. Their foliage covers the lower forest floor, rather like ferns. They are found mainly in tropical zones with their characteristic hot, humid climate. This tropical zone is a highly favorable environment not only for these plants, but also for the many insects and small animals that depend on them. Some of these species, such as Pseuductennis and Nilsionia, look a little like palm trees, with a crown of large leaves that fall and form the trunk. Horsetails are also very common, especially in these same wetlands. These plants can serve as food for a number of herbivores, thus promoting the development of a balanced food chain and a stable ecosystem. It's true that while these lower strata benefit insectivores and small carnivores, we can see here that herbivores also find plenty to eat. Among the horsetails, there are two major species, very popular at the time: the neocalamites and the equisetails. In addition to their great diversity of plants, these forests are home to a wide variety of environments. There are jungles such as one might imagine in the Amazon, swamps and low-lying plants, large clearings where the sun floods the ground with its heat, and coastal landscapes. All these environments form diverse ecological niches, and thus benefit a wide variety of species. It's time to go and meet them. Let's stay on the edge of the forest near this swamp and begin our discovery of Jurassic fauna with a group we've been following for some time now, the amphibians. You were expecting to talk about dinosaurs, weren't you? When you think of Jurassic fauna, you immediately think of dinosaurs. They're the emblematic group of the Jurassic and probably the most important of the animal kingdom during this period. But we sometimes forget that many other species contributed to weaving a veritable ecosystem in which these dinosaurs were able to flourish. Each of these species is part of a greater whole, and each has a role to play in the survival of the others. Dinosaurs were far from the only species to occupy the Earth at this time, and the different groups we're now going to look at undoubtedly contributed to their rise. Let's get back to our famous amphibians. During the Carboniferous and Permian periods in particular, amphibians were the main terrestrial predators, so to speak. Their size was sometimes much greater than we would have expected from the amphibians we know today. By the Jurassic period, they had largely lost this prominent position. Despite their great size, the amphibian population declined considerably, to the benefit of new species. After the Triassic crisis, the arrival of the first dinosaurs and the great diversification of lizards, these animals saw their ecological niche shrink dramatically, all of which logically led to a population decline. When there's no more food and a loss of territory, the species slowly dies. Despite this, a few managed to survive the Triassic period. These even managed to settle comfortably into the Jurassic. So all is not lost for our amphibians. During the Middle and Upper Jurassic, we discover a group that continues to grow to the present day through three major families. These are the Lysamphibians. They form the only surviving group of the amphibian class. This pretty Viorela near this watering hole is a great opportunity to get to grips with the new families of Lysamphibians. It's probably one of the oldest frogs and a member of the Anaran family. Feeding on insects, this little Viorela measures just a few centimeters long. However small, it already displays the physical characteristics of frogs as we know them today, including the shape of its head, large eyes, and muscular legs. Without knowing its group or lineage, it's easy to imagine that it's a primitive frog just by observing its behavior and silhouette. The Lysamphibians include the Anaran family and frogs like the one we've just seen. Lysamphibians also include the Urodal family, i.e. salamanders, and the Gymnophian family, vermiform amphibians also known as apodes or Cecilia. It is these last two families that will interest us now. Still in the Jurassic marshes, an insectivore quite different from Viorela roams the same environment. This time it's one of the very first salamanders, according to the latest paleontological research. Carorus sharovi has all the trappings of a salamander. Its triangular head, upward pointing eyes, and distinctive legs are all distinctive. It measures around 20 centimeters or 8 inches. Its head seems flatter than today's salamanders, and the triangular shape is also more pronounced. Studies of Carorus fossils suggest that this small primitive salamander fed on snails, worms, crustaceans, and perhaps even insects. It thrives in freshwater, where it finds everything it needs to survive. In the early Jurassic, a worm-like amphibian also appeared. We rarely think of this type of morphology when we think of amphibians, but worm-like caecilians are indeed part of this large family. They like damp, dense, warm forests. And in marshes, particularly those of North America, this Eocaecilia finds plenty to do. It measures around 15 centimeters or 6 inches long. It is therefore quite discreet. Unlike the modern caecilians we meet on the continent, this one hasn't lost its legs. If you're observant, you'll see that it has 2 small legs at the front, shortly after the head, and 2 more at the back, close to the tail. Modern caecilians have poor eyesight and often live underground. It is therefore possible that our Eocaecilia micropodia, with its legs and eyes a little more developed than modern specimens, enjoys the great outdoors more than its descendants. Like the other amphibians we met, it feeds on insects of all kinds. It has to be said that over the course of time, they too have diversified considerably. The Diptera group, which includes flies and mosquitoes, has seen an explosion of new species. In this swamp, A Tarsophlebia dragonfly can be seen here. A little further on one of the very common seed plants from the Triassic to the Cretaceous, the Bennettitails Weilandiella, we can also see a new type of dipteran, no doubt a close relative of the cousins. Another small insect, about 6 millimeters long, called Gallimosovelia grioti, can also be seen on the lake. According to the paleontologists who have worked on the subject, this is a water spider and probably the oldest fossil of an aquatic insect of the order Geromorpha ever discovered. This region is ideal for observing insects, so let's stop here for a few moments to take a closer look at a few of them. As we just mentioned, mosquitoes and flies have also undergone a major radiation and population explosion. Climate and the expansion of vegetation have greatly favored the rise of this type of insect. But that's not the only reason. The first insects appeared as early as the Paleozoic era and were mainly terrestrial at first. But the acquisition of wings, and therefore the ability to fly, greatly expanded their range of niches, and by extension, their territory. We find Hymenoptera, including bees, wasps, and ants. Lepidoptera, with 2 pairs of membranous wings, such as butterflies. Diptera, with 2 pairs of wings, such as flies, mosquitoes, and horseflies. And Neuroptera, including lacewings and anteaters. One of the most represented groups of Diptera in the Jurassic is undoubtedly the Stratileidae. This group comprises 2 genera, Stratilia and Vocilla. These flies have wings, contrary to what scientists first thought when studying fossils, particularly those preserved in amber. What led them astray were the fossil remains, without wings. The explanation actually lies in their deciduous wings. Like many modern insects, such as ants, these flies probably lost their wings after mating. Sexual dimorphism is also noticeable in these species. Males have enlarged hind legs. This can be explained by mating requirements, since during their lovemaking the male has to position himself above the female and hold on with his hind legs. Lacewings are neuropterans, characterized by 2 pairs of equal-sized membranous wings with numerous clearly visible veins. Jurassic lacewings have much to teach us. Fossils, for example, have revealed that these insects were already using camouflage as a means of survival, particularly in the larval stage. They blend into the background, make themselves forgotten, and can thus hope to slip through the net of nearby predators. Polystoicotes punctata, commonly known as the giant chrysopod, first appeared in the Jurassic period and was still around until the 1950s to 1960s. Incredible as it may seem, the giant lacewing seems to be back in the news. A specimen was found in Arkansas, USA, in 2012, but it wasn't until 2020 that entomologist Professor Michael Svarla made the connection with Polystoicotes punctata. Insects don't just thrive in the forest. In the aquatic environment, many species are also abundant. Another giant insect. Yes, the Jurassic period also saw insects of rather exceptional size. But fortunately for us, Morrisonepa, unlike the giant lacewing, has now disappeared. Morrisinepa is one of the giant water bugs, like the genus Lothosaurus, and the latter are not renowned for their beauty or gentleness. These insects are extremely painful to bite, injecting their prey with a saliva packed with enzymes that break down proteins. No chance of escaping. Using its proboscis, the giant bug simply sucks up the delicious cocktail of the prepared mixture, a semi-digested bodily liquid from the prey. If Lothosaurus can prey on snails, crustaceans, fish, amphibians, or even snakes, it may be that our Morrisinepa has the same culinary tastes. Other forms of insects are also making their appearance. As we'll soon see, dinosaurs, particularly feathered ones, but also furry mammals, also emerged in the Jurassic. These feathers and hairs offer new opportunities for insects, which can easily attach themselves to their new hosts. Fleas, for example, which are hematophagous insects that feed on blood, made their grand entrance into the animal kingdom to the great displeasure of their hosts. Finally, it was in the Jurassic period that the very first snakes appeared. One of the world's oldest snakes, Diablophis, can be seen here. Diablophis, as well as Portugalophis and Parvoraptor, are primitive snakes. Of course, they have much in common with our present-day snakes, notably the particular shape of their skulls, but they also have a few differences. According to fossil studies, even if the remains are few and often incomplete, paleontologists have reason to believe that these snakes still had their legs. If we summarize the Jurassic context seen in this first part of the video, we can see that plants, insects, amphibians, snakes, and other small animals of the forest and lower vegetation provided a rich ecosystem and varied ecological niches. Each in its own way helped the expansion of the dinosaurs. It's impossible to talk about Jurassic fauna without mentioning dinosaurs, of course, so here we are at last, right in the heart of the Jurassic, facing those famous dinosaurs. They are the emblematic animals of the period. They were very diverse in the Jurassic period, but also very numerous. Remember, dinosaurs first appeared in the Triassic, but their presence was still rather timid. And then, after the crisis, some of them didn't survive. However, the Jurassic did not mark the end of this great group. Quite the contrary. Dinosaurs took over the period and reigned supreme in the four corners of the world. But not everything happened in a day. For them, it all began with the Archosaurs, their common ancestor, an animal clade that includes crocodilians, birds, pterosaurs, and of course all dinosaurs. What all these seemingly different species have in common is a particular feature of their anatomy, the gizzard. This muscular part is used to crush hard food. Over the millennia, Archosaurs formed various lineages, including the one we're particularly interested in now, the dinosaurs. Their emergence was still rather fragile at the beginning of the Triassic period, especially as the first specimens were already facing major difficulties that were to slow down their evolution initially. The biological crisis that marked the end of the first Mesozoic period. First of all, it took time for nature to recover from the obstacles placed in its path. The Jurassic therefore represents an initial period of calm. The Lower Jurassic in particular is a transitional period when nature and the living world gradually reassert their rights. Some species die out, others survive, and that's about it. No major radiation, no demographic explosion of any species. But once the Lower Jurassic is over, the Middle Jurassic is marked by a great explosion of diversification and the development of numerous species. This demographic and radiative explosion continues into the Upper Jurassic, and the vast majority of these species belong to the vast dinosaur family. From the Middle Jurassic onwards, the era of the dinosaurs was truly established. Adaptations, radiations, evolutions, diversifications, demographic explosions, everything came together for dinosaurs to become major players in the Jurassic period, and more broadly, in a large part of the Mesozoic. While two major groups of dinosaurs had already appeared in the Triassic, the diversity of ornithischians and saurischians exploded in the Jurassic. Among the ornithischians, mainly herbivores that moved in herds, three major groups appeared that were to expand the dinosaur family: the theriophores, the ornithopods, and the marginocephali. The suborder theriophores means shield-bearer in ancient Greek. This gives you a clue as to what makes this group so special. Although they are mostly quadrupedal herbivores, their distinctive feature is their backs, which are armored with bony plates, spikes, or spurs, depending on the species. As we saw when discussing vegetation earlier, there were several strata in the plant cover. Low-growing plants were one of the favorite foods of the dinosaur that now awaits us. It's a very popular dinosaur, recognizable by its famous bony plates alternating in two rows on its back. This is the famous Stegosaurus. His body is quite stocky, but his head is rather small compared to the rest of his body. Scientists are still debating the usefulness of Stegosaurus's bony plates, but several interesting hypotheses have been put forward. One of these is that they may have been used as a deterrent, or even a defensive device against predators. Stegosaurus, especially juveniles, were preyed upon by dinosaurs such as Allosaurus and Ceratosaurus. Recent research also suggests that these plates were gorged with blood and therefore sported a bright red hue that could also greatly intimidate any bold predator. But it's also possible that these famous spikes are simply a courtship tool, or that they have a thermoregulatory function. If they are also vascularized, they can act a bit like a solar panel, capturing heat and transmitting it into the bloodstream to warm the animal's body. But in other circumstances, such as when the animal shakes its plates, it can actually cool its body. In other words, he's got both air conditioning and heating at his fingertips. To get around, he had a good footing on his four legs. It has 3 little toes on its front legs and 5 on its hind legs. There are pads under each of them. On the other hand, his posture is a little unusual. If you look at its silhouette, you'll see that its front legs are shorter than its hind legs. The tail is well above the ground, while the head is relatively low. This morphology can be explained by the type of food it consumes, since it feeds on plants low to the ground. It has a beak and small teeth that enable it to cut and chew plants. Another type of dinosaur had bone plates, but they are quite distinct from those of the Stegosaurus. Here's a Nodosaurus, a Borealopelta to be more precise. As you can see, it has a bony plate that forms a sort of band, a bone nodule, hence its name, nodule lizard. The fossils of this Nodosaurus have enabled scientists to study, among other things, the remains of its stomach. We therefore know that it was a great gourmand, particularly fond of the ferns that carpet the forest floor. It must have consumed large quantities to meet its colossal energy requirements. The animal weighed over a ton and was almost 5 meters long. To facilitate digestion of these fatty ferns, the animal also swallowed the occasional stone. As its jaw wasn't much help when it came to chewing, it had to use gastroliths to make the most of the plants it ingested. Let's take a look at one of these cousins, a dinosaur best known for its distinctive tail. You may recognize it from the Ankylosaurus. It's more massive. Some 8 meters long, 2 meters or 7 feet high, and almost 4 tons rest on those 4 impressive legs. Unlike other members of the Theriophora family, he doesn't just have a body covered in thick armor. It also has a large club at the end of its tail. The last caudal vertebrae fuse together to form the club. He also has tendons that enable him to direct and manipulate this club, in particular, to give it a certain impulse to parry or deliver blows. This asset enables him to defend himself against the predators that are rampant in the region where he lives, the riverside forests. But when attacked, he also tended to flatten himself on the ground and wait for the right moment to use his club. Do you have any idea why he adopts this peculiar behavior? If you look closely at his breastplate, you'll see that it covers a good part of his body from head to tail, but not his belly. This is his Achilles heel, his weak point. It's his Achilles heel, his weak spot, and he needs to protect it first if he's to survive in battle. Another peculiarity of this dinosaur is that it also swallowed stones to facilitate digestion of the plants it ingested. This is very common in dinosaurs that don't chew well or have sufficiently developed teeth to do so. Let's take a look at another type of dinosaur, the Ornithopoda. They may not be the most familiar to the general public, but they are one of the most successful and longest-lived dinosaur lineages. Just look at the great diversity of subgroups that define this branch. Frabrosauridae, Heterodontosauridae, Hypsilophodontidae, Iguanodontidae, Hadrosauridae, and each of these subgroups has a large number of species. This time, the ornithopods, unlike the theriophores, are herbivores for the most part, but walk more easily on 2 rather than 4 legs. Fabrosaurs are the oldest ornithopoda, but also the most primitive. They were very small compared to other groups, between 60 and 120 centimeters, or 24 inches and 47 inches. Heterodontosaurs were already a little more developed. We see the horny beak appear, but also more complex teeth. Heterodontosaurus, for example, sported 3 types of teeth: sharp teeth that formed a real jaw with fangs, and wide teeth for crushing plants. A new specimen of this group was discovered in 2012, even though it was discovered much earlier. Pegomastax africanus is an astonishing little animal, measuring 45 centimeters or 18 inches long. While its skull is reminiscent of a parrot, its body is more like that of a porcupine and its teeth more like those of a small feline carnivore. Despite its sharp fangs and canines, it's definitely a herbivore, and perhaps even frugivorous, to be quite precise. According to descriptions by Paul Sereno, an American paleontologist from the University of Chicago, the fangs helped it to pick up plants, particularly fruit, and the small teeth in front of the canines were used to cut up the plants. It's also possible that these teeth were used to defend against predators or to protect their territory, for example. The Hypsilophodontidae group is best illustrated by Hypsilophodon. They can be found in every corner of the globe. They are larger than the previous ornithopods we have encountered. Hypsilophodon can reach 2 meters or 7 feet in length and weigh around 25 kilograms or 55 pounds. Its beak, quite similar to that of a turtle, enables it to cut the vegetation on which it feeds. As for its gait, its skeleton seems to indicate that it is undoubtedly a good runner. But the latter is of particular importance here, not because of its running prowess, but because it may have given rise to the next two lineages, the hadrosaur and the iguanodont. This time, the latter evolved mainly on 4 legs. However, it's not impossible that they were able to run on their 2 hind legs to escape, for example. Iguanodon was the second dinosaur to be discovered in history. The name given to this group is linked to their teeth, which are quite similar to those of the iguanas we know today. They are savanna dwellers. It feeds on ferns, but also on arborescent plants such as conifers, cycas, or ginkgos, for example. He was able to get to grips with them, as he was able to chew for a long time. We mentioned this earlier in connection with vegetation, and it's important to make it clear here. As you can see from the presentation of these first dinosaur species, all the plants we have seen above provide an ecological niche for dinosaurs that are very different from one another. Ankylosaurs like low-growing plants like ferns, while others like Iguanodon are better equipped and taller, and can take advantage of arborescent plants like conifers or ginkgos. Let's close this little plant parenthesis and pick up where we left off with the study of dinosaurs, and iguanodonts in particular. With research and discoveries evolving day by day, each time revealing a new facet of our distant history, the genus Iguanodon is in the process of being redefined, if we can put it that way. Certain species of Iguanodon, for example, are sometimes given different names, such as beryllium, dolodon, Hypsilospinus, Pterylion, or Wadhurstia. Nevertheless, let's try to establish some general characteristics of the genus by studying Iguanodon bernissartensis. At 5 meters or 16 feet high and 9 meters or 30 feet long, it weighs almost 5 tons. This makes it one of the larger dinosaurs. This herbivore nevertheless had plenty of predators. To defend itself, it's possible that its thumb was a great help. At the very least, it enabled him to curb the ardor of his adversaries. In fact, his very sharp thumb turns into a dagger against carnivores when our iguanodon feels threatened. Another specificity of the genus is its famous duck-like beak and prehensile tongue, which enable it to tear up vegetation. The subject of its limbs and gait has long been a matter of debate among scientists. Is it a quadruped, a biped, bipedal only in its prime, or when juvenile? Although a few discoveries, notably in 2000, have cleared up a few mysteries, the vagueness is still quite relative. Its long, heavy tail is the main reason for questioning its approach in the first instance. To understand ancient species, we rely on our knowledge in comparison with current species. Here, scientists see some semblance of a kangaroo. Its strong, muscular tail could provide support for the animal, which would then walk on its two hind legs. But in the 2000s, paleontologists brought to light an essential new feature of the iguanodon skeleton. Its caudal vertebrae are connected and rigidified. The first thesis no longer holds. It would seem that the tail is more a kind of balance beam, or even, depending on the situation, a counterweight. Although it moved mainly on its four legs, it's not impossible that it also moved from time to time on its two hind legs, perhaps to run and escape. The strength of herbivores to defend themselves lies above all in the horde. In a group, you're stronger. They protect each other. Iguanodons were no exception to the rule. They may also have formed part of an interspecies horde, alongside ankylosaurs, for example, to increase their chances of curbing the ardor of nearby predators. Especially as these dinosaurs did not feed on the same plants, they had everything to gain and nothing to lose by joining forces to preserve their safety. Let's take a look at the last group of ornithopods, the hadrosaurs. According to certain paleontological studies, hadrosaurs are descended from iguanodonts. It's true that they share many common characteristics. For example, they share the duck beak. Hadrosaurs have a flattened skull, enlarged in the shape of a beak to enable them to reach and gather leaves from trees in tropical forests. This ability and their dentition are assets. They will thus be favored in future evolutionary radiations over other herbivores that need gastroliths, for example, to digest plants. Hadrosaurs were fairly widespread in the Jurassic, but will be even more so in the Cretaceous. They settled all over the planet, in Asia, Europe, and North America. In fact, it was in this region that a new specimen of the genus was discovered in 2021 by students at the University of Reading in Canada. Many types of dinosaur have already been found in the region, but this time, what makes this particular fossil so unique is its age, its state of preservation, and in particular, its fossilized skin. There's no doubt that these latter elements have a lot to tell us, especially since this Hadrosaurus is thought to be a juvenile. Paleontologists may also learn more about the growth and development of these dinosaurs. Let's take a look at our final group of ornithischian dinosaurs, the marginocephalons. The marginocephalons are a special clade of dinosaurs. Although they are all herbivores, they can be bipedal or quadrupedal. What they have in common is the narrow horizontal ridge of bone at the back of their skulls. This group was to develop more extensively in the following period, the Cretaceous. But some of its members can already be seen on the Jurassic Plain. One of the best-known groups of marginocephalans is the ceratopsians. They were the group's first members. They appeared at the end of the Jurassic in present-day China. Unlike their future descendants, our first ceratopsians did not yet have the famous ruff like that of the famous Triceratops. They have an armored body and a rostral bone in the jaw. This beak-like bone enables them to tear up plants with disconcerting ease. This jaw can be seen in action in Psittacosaurus, for example. Bipedal, it is the size of an antelope. Like our modern rodents, its teeth are self-sharpening. They wear down to create a sharp edge that can cut through the toughest plants. Despite its effective jaws for cutting plants, it is not yet very well equipped in terms of digestion. It must therefore use gastroliths to crush food in its digestive system. Many Psittacosaurus fossils have been found. In some cases, up to 50 gastroliths have been found. Paleontologists believe that these gastroliths may have been stored in the gizzard, the muscularized part of the stomach. Our Psittacosaurus closes the chapter on ornithischians. Now it's time to discover the member of the second dinosaur clade, the Saurischians. In the Jurassic, the Saurischians also largely continued their evolution. The branch led to birds. Within this group of dinosaurs, two main subgroups soon emerged: the theropods, mostly bipedal carnivores, and the sauropods, large quadrupedal herbivores. Let's start with the theropods, which underwent a meteoric diversification. As we saw earlier, many herbivores populated the Jurassic soil. Herbivores meant prey, and prey meant predators. While herbivores were numerous, carnivores were also widely present. One of the best-known Jurassic predators is undoubtedly the Allosaurus. Often confused with Tyrannosaurus, Allosaurus is one of the great predators of the Jurassic. It has a huge jaw, crenellated and curved teeth that enable it to tear flesh, and if it loses a few of them in an over-aggressive attack, they soon grow back. In addition to this extraordinary dentition, he also has short but robust forelegs. They are useful for grabbing prey and holding on tight. He also uses them to butcher his victims. The hind limbs are longer, but just as vigorous. They are also equipped with claws. Carnivorous and perhaps occasionally a scavenger, Allosaurus can also hunt in groups to attack large Jurassic herbivores. There's no stopping it. This bipedal dinosaur is perfectly equipped to be a top Jurassic predator, but it's not the only one to covet this position. Let's take a look at the Megalosaurus. At 7 meters or 23 feet long and 3 meters or 10 feet high, it's quite imposing. It was the very first dinosaur to be described and given a name. In fact, it means great lizard in ancient Greek. It has many of the same characteristics as the Allosaurus. These include short, clawed forelimbs, longer, sturdier hind limbs, and a crenellated blade-like jaw, it was one of the most feared predators of the Jurassic period. In another genre, there are also dromaeosaurs, which began to emerge very slowly in the Jurassic, but would become more widely established in the Cretaceous. This time, we're dealing with a medium-sized carnivore. Its distinctive feature is that it is covered in feathers. At least that's what the latest research has revealed about it. It shares many characteristics with primitive birds. Body shape, feathers, legs, and the famous claw on the second finger are just some of the bird-like features. This group of dinosaurs brings us to the avian dinosaurs, such as Archaeopteryx. Archaeopteryx is another type of feathered dinosaur. It has all the attributes of certain birds. However, its reptilian side cannot be ignored either, with characteristics that define it as a small bipedal dinosaur akin to a Compsognathus, for example. This strange bird is undoubtedly the one that makes the link between dinosaurs and birds. With its claws and long tail helping it to maintain balance, it can easily hunt insects and small animals. Speaking of small animals, isn't the Jurassic known as the Age of Giants? So what's really going on? If we look at the fossils of the largest known dinosaurs, a certain number can be placed in the Cretaceous period rather than the Jurassic. So why do we refer to the Jurassic as the Age of Giants? Is it a linguistic error? Misinformation? A popular misconception? No. The Jurassic can indeed be recognized as the era of the giants. The huge, long-necked sauropods were very numerous during this period, with a wide variety of species, justifying the term Era of the Giants. Let's go and meet them. Despite their immense size, we have nothing to fear. These giants are herbivores. Incidentally, to popularize the history of dinosaurs, the term herbivore has been used until now, but it's better to call them vegetarians. Grass didn't appear until the following period, the Cretaceous. With that in mind, let's take a closer look at these famous Jurassic vegetarians. The first one we're going to meet is a Diplodocus. According to scientific estimates, Diplodocus halorum measured 30 meters or 100 feet and weighed 24 tons. Its neck is almost 6 meters or 20 feet long, enabling it to reach food inaccessible to many herbivorous dinosaurs. It can reach the tops of trees, such as conifers, but it can also extend its neck and feed on aquatic marsh plants or horsetail beds. Its extremely long tail is also very useful. Made up of 80 caudal vertebrae, it acts as a counterweight, but can also be a powerful deterrent to predators. According to a hypothesis put forward by certain paleontologists, this massive tail also plays a role in courtship. To demonstrate their power, males would slam this giant whip to the ground. They estimated that the noise generated during these parades could have reached 200 decibels, a sound more powerful than a plane taking off at less than 100 meters or 330 feet. Diplodocus shares its territory with other gigantic animals, such as Bothria spondylus, another Jurassic mastodon classified as a sauropod, measuring almost 20 meters or 66 feet long. The Brachiosaurus genus is undoubtedly one of the best known to the general public. The full name of the genus's only species is Brachiosaurus altithorax. It too is one of the largest animals ever to walk the earth. It measures around 25 meters or 82 feet in length, and no less than 12 meters or 40 feet in height. Each of the vertebrae in his neck measures 70 centimeters or 28 inches, and he has 12 of them. Despite his oversized body, he has a small head. His guilty pleasure? The famous large trees we saw in the forest in the first part of the video, but also the cycads with their tender, tasty leaves. Despite its immense size, a serious competitor will soon be arriving in the Cretaceous, the Titanosaurus. After a long stroll through these Jurassic forests, it's time to see what's going on below sea level. The ocean is teeming with extraordinary creatures. Since the Triassic, the marine world has also undergone many upheavals. At first glance, terrestrial fauna is rich and diverse. But what about underwater life? Is underwater life also flourishing? Let's find out. In the heart of the Jurassic Ocean, of course, we find many of our famous shell animals, which form one of the bases of the food chain. Some of them are very special. We first encountered them in the Triassic, and they continued their reign of the shallows during the Jurassic. These are the ammonites. They are so numerous and diverse that scientists consider them to be stratigraphic markers. In other words, depending on the fossil species found, they are able to determine the age of the soil. Ammonites are therefore abundant in the ocean, providing a veritable food source for small and medium-sized predators. But ammonites are not always easy prey. At least some species are undoubtedly difficult to attack by small predators. Indeed, paleontologists have unearthed an ammonite measuring almost 2 meters or 7 feet in diameter. While these cephalopods are literally swarming all over the world's waters, they are far from the only ones to roam these marine territories. Predators are on the prowl. In the Triassic, we were able to see some great marine reptiles, such as the Nothosaurus. Unfortunately for them, despite their impressive power, they were unable to survive the crisis that marked the end of this period. The majority of the marine reptiles of the time, such as Hooposuchians and Thalattosaurians, suffered the same fate. Only one group managed to defy the climatic changes and geological obstacles imposed by nature during and after the Triassic crisis. It's the ichthyosaurs. Thanks to the latest discoveries by paleontologists, we now know that these marine reptiles were warm-blooded animals and that they gave birth to their young in the open sea. Skeletons of embryonic ichthyosaurs have been found inside the bodies of adult individuals, sometimes even in a position indicating that they were ready to give birth. Their size varied greatly from species to species. The smallest measured barely 1 meter or 3 feet in length, but the largest specimens could reach 20 meters or 66 feet. If they are often compared to dolphins, it's not just for their elongated snouts and sharp teeth, but for the similarities in their way of life. They are adapted to a pelagic lifestyle, but can also descend to the depths. They feed on fish and ammonites. Despite their formidable rise and great adaptability, the ichthyosaurs were to face stiff competition from the massive arrival of the plesiosaurs. Plesiosaurs were another major group to emerge in the Triassic, completing the large family of Jurassic marine superpredators. They have small heads, long necks, and bodies similar to turtles. They are also characterized by a short tail and 2 pairs of large fins. Plesiosaurus is a typical species of this order. It measures up to 5 meters or 16 feet in length. Its neck alone accounts for a large part of its length. Contrary to popular belief, its neck was not very movable. It was even rather stiff and unable to bend to feed, as swans, for example, can. It occupies more or less the same ecological niche as our Ichthyosaurus. In other words, it gradually took its place. It fed on fish and small prey, such as belemnites, animals belonging to the cephalopod clade. A fetus was found in one of the fossils studied, enabling scientists to confirm that plesiosaurs were viviparous. The female gave birth to just 1 offspring at a time. Guided by her maternal instinct, she took care of him during his early years, taking the time to teach him everything he needed to know, such as how to find the most beautiful belemnite specimens. This way, he could fend for himself later on in this blue immensity. The Pliosaurus is another of the most ferocious marine reptiles found in waters all over the world. It even terrorizes other marine reptiles, such as our Ichthyosaurus. Its jaws, armed with 130 sharp teeth, are enough to make the ocean tremble with fear. Long and razor-sharp, they kill with 1 clean stroke. Its size is matched by its formidable dentition. It could reach 13 meters or 43 feet in length. Its swimming legs, 4 powerful limbs, propel it at high speed so that it can charge at its victims. The Pliosaurus is rightly nicknamed the T-Rex of the seas. Pliosaurs aren't the only ones to conquer the ocean. Crocodiles are also taking to the sea. To illustrate the crocodilian order, I suggest you discover Cricosaurus bambergensis. It lives in shallow seas, particularly near archipelagos, where it finds everything it needs to survive. Contrary to the image we have of crocodiles, whose ancestor it is, it shares some similarities with other aquatic animals, such as dolphins. In particular, it has a caudal fin and limbs that are more akin to swimming legs than to functional legs for terrestrial mobility. Rather voracious, reactive, and fast, it doesn't hesitate to pounce on squid or fish. During the Jurassic period, a new lineage of marine turtles appeared in the aquatic world. Fossil remains of sea turtles have been discovered in Bavaria, southern Germany. The Solnhofia parsonsi turtle. This isn't all that surprising when you consider that the region at the time was, unlike today, a kind of tropical archipelago. The sea was shallow and populated by sponge reefs of all kinds. While it's easy to recognize a turtle's silhouette, a few details show that they were not yet as evolved as our modern-day turtles. Their legs, for example, are not yet paddle-shaped, but rather finger-like. This means they can move more easily along the coast. Secondly, unlike our turtles, they are not equipped with the famous salt-eliminating glands. They do, however, have the same pointed snout and triangular head. Other species, notably those in the Plesiocelus and Thalassemus genera, populate the archipelago. These turtles had to be wary of a powerful predator that roam both fresh and salt waters. Hypodus lived in the same geographical areas as certain marine reptiles and crocodilians. While the latter was undoubtedly preyed upon by marine reptiles twice its size, this did not prevent it from finding plenty of prey to sink its teeth into. It is a durophagous predator, meaning that no hard shell or prey frightens it. It feeds not only on belemnites, but also on other small prey, thanks to its specialized teeth. Its teeth are wide and flat, designed to crush and crush. They move quickly with their well-developed pectoral fins, making them a rather active and voracious predator. To reproduce, hybodonts lay their eggs in the water. A sort of spiral egg case was attached to the marine vegetation by a small tendril. We'll now leave the aquatic world behind us on the images of this little chord of life and head for the sky. As we already saw when we looked at the Triassic period, the wide diversification of insects and their growing population in the forest heights, as well as the presence of large predators on the ground, favored the expansion of flying lizards. During the Triassic period, one of the first groups of pterosaurs, the Rhamphorhynchids, appeared. Small in size, they were still quite primitive. But the Jurassic changed all that and shook things up a bit among these sky gods. Whereas in the Triassic we could admire Eudimophodon with a wingspan of around 1 meter, by the Jurassic, species such as Rhamphorhynchus with a wingspan of 2 meters or 7 feet were appearing. But it's far from the only one to roam the skies. One of the largest Jurassic pterosaurs is Dirkgiakonath with a wingspan of 3 meters or 10 feet. The Middle Jurassic also saw the emergence of a new family of pterosaurs. They are called pterodactyls. They can be distinguished from the more primitive pterosaurs by their shorter tails, absent fifth toes, and fewer teeth. They are generally smaller than our previous pterosaur specimens. Their average wingspan varies up to 1 meter or 3 feet in length, but some reached a wingspan of 3 meters or 10 feet in the Jurassic. These carnivores feed on fish, but also on small land animals on occasion. To help them in their predatory task, they are equipped with 90 small, fine, conical teeth. Large numbers of pterosaurs appeared in the Jurassic period. Although species diversified and developed even more widely in the Cretaceous, it is clear that they were beginning to make their mark on the Jurassic sky. If the pterosaur branch is diversifying to such an extent, it's because numerous niches among the sky gods are taking shape. To find their place, they had to adapt to their environment according to their needs. Pterosaurs come in all diets. Insectivores, of course, but also piscivores, filter feeders, and duraphages in the marine world, and carnivores, herbivores, and omnivores on the mainland. There are also changes on land, with new small mammalian animals, in addition to the ever-popular dinosaurs that marked the history of the Mesozoic, mammals also made a timid appearance as early as the Triassic and continued their slow evolution during the Jurassic. Indeed, amidst the thousands of dinosaurs, it's hard to find a place for mammals in the Jurassic living world. Nevertheless, mammals did not give up. Biological crisis or lack of adaptation, vacancies are forming in certain environments. One man's misfortune is another man's gain. These ecological niches were soon exploited by newcomers. During the Triassic, in the center of Pangaea, the climate was rather dry, but following the breakup of Pangaea, the climate became hot and humid. As a result, vegetation flourished, and as we've seen several times, lush jungles soon covered a large part of the land, benefiting a large number of animals: dinosaurs, reptiles, pterosaurs. But not only. Some species will adapt and take advantage of this particular environment to occupy a tropical and arboreal environment. These include small, arboreal animals such as the Shenshu and Jianshu genera, and mammals. Shenshu is a small animal measuring 18 centimeters or 7 inches, with a long tail of 20 centimeters or 8 inches, and a weight of around 300 grams. Its prehensile tail is one of the features that led paleontologists to classify it as an arboreal animal. The Jianshu genus comprises 2 species, the linglong and the sonjie. They differ from the Shenshao genus despite some similarities. The first incisor is distinctly smaller in Jianshu, and it also has ovoid molars. Measuring around 20 centimeters or 8 inches long, it weighs just 40 grams, according to scientific estimates. Linglong is slightly larger, weighing around 80 grams. What's most striking about these 2 very special genera is not so much their arboreal nature, even if this shows a formidable adaptation within the mammalian lineage. It's also the emergence of the characteristics of the first mammals. In addition to their dentition, notably the mandibular joint characteristic of the mammalian clade, we can also see by observing their fossils that the skeleton has 3 very specific bones in the middle ear. This means they were equipped with eardrums, which transformed air vibrations into sound. This shows that mammals are able to establish themselves over the long term by occupying specific ecological niches, diversifying, adapting, and evolving. Many other surprises await us as we discover the mammalia forms, and in particular, the mammalia, the mammals that gave rise to our contemporary fauna. But that's another story, another period, another journey. See you in the Cretaceous to find out.